doing work over charge. This is they're all the same now. We've removed the dependence on the charge that we're moving around, and all this quantity that's left, work divided by charge, that only depends on what's creating the field. And that hasn't changed. That only depends on the field, and that hasn't changed. So this is going to be very useful. The problem is that we don't have a mechanical counterpart. We never did potential in mechanics. Potential is not potential energy. They're two different things. That's part of the confusion. I told you we're going to come up with a potential energy for the electric field because it's a conservative field. We've done potential energy with gravity, right? We've done potential energy with springs, so that's nothing new. We're going to do potential energy with electric forces. But we've never done potential. Potential is different than potential energy. Electric potential is this new term here. It's the work divided by Q. And it only depends on the field. And the reason we do it is because we might be moving. Let's picture this. Picture a waterfall. And maybe we're doing this. I'm trying to come up with a mechanical analogy. So we have water. And as it comes out of the faucet here, it turns a wheel. And it does some work, right? And then what happens? It pulls up. And then we have a pump. Okay, so the amount of work that the water is doing, right, turning that wheel, we can figure out how much work we can get out of the water, depends on what? Depends on the flow of water. So if we have just a little bit of water coming out, we get a little bit of work out. If we have a lot of water, we get a lot of work out. And if the flow of water is always changing, then it becomes a hassle to figure this out, right? Every time we figure it out, an instant later it's different because the flow of water has just changed. So we want to divide by the flow of water and say that this setup has a certain potential. And then I can just multiply by how much water is flowing, and I get my work being done, my energy, my work being done, and that tells me how much energy I get out at that instant. So I don't want to have to recalculate this all the time. This is particularly important in circuits, because this is like a circuit, right? You've got electric charges running through your circuit, and the flow of charges changes in our circuits, right? Because it's an AC circuit. It's small, it gets bigger, it goes to zero again, it goes in the opposite direction, it goes to zero again, it goes in the other direction. The flow of charges is always changing. So we want to eliminate the charge so we can look at a circuit and kind of see what's going to happen. And then if you want to know how much power is being delivered to a light bulb, you put in the effect of the charge at the end. All right? So that's why we're getting there. But because we don't really do this in mechanics, we don't have a mechanical equivalent for potential. So it's a little bit of a new thing. That's one problem. All right. So let's take a look at what this says here. It says the electric potential difference between 2 points, W and X, is defined by negative the work done divided by Q. And potential, like potential energy, it's not potential energy, right? But like potential energy, What's important are differences. Just saying something is 40 volts doesn't really mean anything. We have to know it's 40 volts above this other point, right? We have to know a difference between two things, just like potential energy. All right, so a potential difference is negative work done by the field over the charge. And that's the charge that we're moving, right, from point A to point B. All right, so number 3, what does it say? Does this quantity depend on the magnitude of the charge used to measure it? What's the answer? No. That's why we're dividing it out, right? We don't want it to depend on the charge. We only want it to depend on the field. That's the whole point of potential, electric potential. So it does not depend on the magnitude of the charge. We've divided it out. How about the sign of the charge? If we change the sign of the charge from positive to negative, what happens to the work done? It changes from positive to negative, right? Think about our little test case here. Just think of a simple case. Here, we have a positive Q and a positive test charge, and it's moving to the right, and the force is to the right, so the work done is positive, right? Work done by the field on that little charge is positive. Now if we change the sign, we have a positive Q and a negative Q naught, and it's moving this way. What direction is the force on Q naught? The other way, right? Because opposites attract. And so the work done in this case is negative. It's moving to the right, but the force is to the left. We get negative work done. So the work has changed sign. Now we're going to divide by Q naught, which is a negative now. So what do we get for our potential difference? The same thing, right? It does not depend on the charge we're moving from point A to point B. It only depends on the electric field that exists between points A and point B. So it doesn't depend on the magnitude of the charge, doesn't depend on the sign of the charge. The potential difference between those 2 points only depends on the field. It doesn't depend on what we're moving from point A to point B. We've divided that out. Sign, magnitude, everything. Okay?